Hello, and welcome to the ERI Technical Leadership Panel. Today's panel is intended to be an open discussion among industry experts about current technology challenges facing the commercial semiconductor industry and the defense industrial base, including the future trajectory of commercial and defense electronics, the innovation path from R&D to products, and major R&D areas with potential for research partnerships between the commercial and defense sectors. In addition to these technology issues, we are clearly facing many challenges today from the global competition that we would like to explore, including the role of foreign investment, access to leading-edge manufacturing, workforce challenges, and the need for secure supply chains and the protection of intellectual property. It's really a lot of ground to cover. Thank you for joining us. I'm Dave Anderson, President of Semi Americas, and will be your host and moderator for today's discussion. But more importantly, to address these questions, we have four panelists with tremendous experience from across the industry. I'd like to introduce them to you right now. First, we have Ms. Annabel Flores, Vice President of Electronic Warfare Systems for Raytheon Intelligence and Space. She oversees the overall strategic direction and operation of a diverse portfolio of electronic warfare products, such as the U.S. Navy's Next Generation Jammer and the U.S. Army's Electronic Warfare Planning and Management Tool, as well as Raytheon's high-energy laser systems and applied signal technology. Throughout her career, she has held various positions in business development roles at Raytheon's corporate team and with its intelligence, information, and services business. Welcome, Annabel.
Thank you.
Next, we have Doug Bostrom, Vice President of Engineering for Infrastructure and Defense Products at Qorvo. Qorvo is the leading GaN RF supplier for the defense and cable industries. Prior to joining Qorvo, Mr. Bostrom held several senior technical leadership positions at Raytheon. He brings more than 30 years of experience in the defense industry, including product management, engineering, developing complex RF systems, and components. Welcome, Doug.
Thank you, David. Appreciate it.
We also have the pleasure with us to have Dr. Michael Mayberry, Chief Technology Officer at Intel Corporation. Since joining Intel in 1984 as a process integration engineer, Mike has held a variety of technology development positions across the organization. As CTO, he's a Senior Vice President and General Manager of Technology Development, where he is responsible for the research, development, and deployment of next-generation silicon logic, packaging, and test technologies that will produce future Intel products. Welcome, Mike.
Thank you, David.
And finally, we have Dr. Ahmad Bahai, Senior Vice President and Chief Technical Officer of Texas Instruments, responsible for guiding innovation, corporate research, and the Kilby Labs. Dr. Bahai is an adjunct professor at Stanford University and an IEEE Fellow. Throughout his career, he's held a number of leadership roles, including Director of Research Labs and Chief Technical Officer at National Semiconductor, and a Technical Manager of Research Group at Bell Laboratories. Welcome, Ahmad.
Thank you, Dave.
Okay, so to get started, we want this to be a discussion amongst the experts. So from a format standpoint, I'll frame a topic and pose a question or two and let the entire panel weigh in on each area. So let's start high and broad and then work our way down. So clearly, industry drivers have shifted from national security and defense in the early days to business computing, personal computing, to mobile phones, and now to the cloud. The global semiconductor market is now driven primarily by consumer demand. I guess the first question is, what consumer trends do you expect to drive microelectronics development over the next 10 years, and how might that influence the semiconductor market? Ahmad, would you like to start?
Yes, sure. Very interesting question, Dave. Actually, we see dynamics of consumer market is driving a lot of recent innovations. And as always, it's kind of hard to predict what's going to happen for the next 10 years. But what is clear is that a lot of interesting innovations that now is happening in consumer market quickly and a relatively short period of time translates to opportunities on in industrial, in automotive, in aerospace, and many others. That is partly because of the fact that semiconductor technology is becoming so efficient and so affordable that you can do a very high performance photonics on silicon, or even radar or something technologies that used to be extremely expensive on a single chip and potentially deployed in many consumer applications. I remember when I was working on some early radar technologies, maybe 20 years ago, it used to be like a massive system with a very expensive components, and now it's a single CMOS chip that can handle very high performance, 78 to 81 gigahertz kind of solution. So we see a lot of those technologies are quickly adopted in consumer market and driving innovation. And the boundaries between consumer and professionals are kind of blurring. One great example of that is what's happening in AR and VR. It used to be kind of like a luxury for gaming or some specific applications, but now thanks to some of the technologies on a structured light and MEMS technology in optics, we see that it's becoming a professional tool for many applications like remote monitoring, installation, and many other applications. So it quickly translated from a consumer to a professional medical or industrial applications. Some of the areas that I think has a lot of potential for growth is what I call it man-machine interface or human-machine interface, HMI. As I said, I mean, things like AR, VR, we can see that it's becoming more relevant in a lot of not only consumer, but industrial, automotive, and medical applications and aerospace. The structured light, which used to be a quite heavy industrial application, now is very much possible in a consumer device. We see even some smartphones. NLP still has a lot of room for growth. And in general, I see that this cross-pollination of technology and innovation drives a lot of opportunities in consumer and other market segments.
Thank you, Ahmad. Mike, would you like to weigh in on that?
Sure. Since Ahmad picked on interfaces, let me start there. I think one of the trends that we see are that people are increasingly impatient. You know, the whole notion of internet time. I need it now. I want my deliveries today. All of that ties into getting the stuff that you want, whether it's entertainment, whether it's information, whether it's placing an order in a system, as quickly as possible. So from a technology point of view, working on latency, working on distributing content, distributing compute closer to the point of consumption. I think that's one big trend. I think a second big trend is the notion of relevance. You know, there was an old song of 500 channels and nothing on. Well, the internet is 100 million channels or more, and finding the right content that you're looking for at a given point in time, it doesn't necessarily have to be the exact thing, but something that's relevant to you is the other piece of the puzzle. Now, given the constraints of latency, we can't sit and calculate all day on figuring out what that is. But the techniques of AI are a start down that direction. Coming up with faster ways to do AI, or at least good enough AI, I think is the other important trend.
Great, thank you. Annabel, how about from your perspective?
Now, to add a little bit more to what they both said, a lot of consumer electronics are all about making it smaller, making it cheaper, getting it into the hands of consumers faster. And we're seeing similar trends within the defense industry. It really is about more processing power, more capability, higher bandwidth. All of this really combines to smaller packages that if you look at what is being deployed, what capabilities are needed, it's all about smaller swap C. So it's those similar trends that we're also looking at to help shape and meet our needs.
Thank you. And Doug?
Yeah, so from a Qorvo perspective, we're predominantly in radio frequency semiconductors. So a lot of gallium arsenide, gallium nitride, and silicon as well. And we continue to see the need to add capability and drive higher levels of integration, partly from the silicon chips, but also just in the overall subsystem. And so a perfect example of that is your cell phone, going from 4G to 5G with millimeter wave, adding lots of functionality into the device, but you're not going to grow the size of the handset. And battery life is still, you know, a primary driver. So we've got to innovate. We've got to work higher levels of integration. Smaller footprints, somebody else said that, continuing to shrink the functionality that we put into a device. The other thing we see, though, is as in the RF side, as data rates continue, and the thirst for high data rate, bandwidth, low latency continues, frequencies are pushing up. And so, we see now Wi-Fi, for example, added a 6 gigahertz channel and is looking at more. Cell phones, 5G has added millimeter wave. And, there's propagation challenges there, there's range challenges there, but it's all in a quest for data rate and serving a large group of users simultaneously.
Thanks. And I guess to add on to that, Doug, we talked about latency and access to content and bandwidth and speed, and we're seeing a rapid global development of 5G infrastructure and future for RF communications. What do you see that will bring from the commercial markets to the defense space?
So a lot of that, so defense will have similar needs, similar latencies. A big part of 5G is not so much the, say, video bandwidth, that kind of thing. It's really the Internet of Things and the connectivity, the number of devices in an industrial setting and a military setting that you can host at the same time. And so while it's a great platform, obviously there's a layer of security that's got to be addressed to make sure that it's assured communications and doesn't go where it's not intended, nor is it disruptive. So I think a lot of there's a lot of millimeter wave array work in the defense and government space right now as 5G pushes into millimeter waves and has a very constrained footprint, say in a cell phone, that kind of thing. I think the technologies that are being developed will be very quickly leveraged into the military sector.
Fantastic. And Annabel, can you comment on that as well?
Yeah, I'll pull on those threads that Doug just mentioned, right? Everything that we're talking about in terms of getting access to data down to the decision maker is about connecting to the Internet of Things and providing that information and capability in a digestible, actionable way. So that does mean helping to resolve a lot of these issues, helping to get the data to that point faster in a way that's quickly consumable. AI was brought up earlier as a very key thing that's going to be able to enable some of these, but all of these pieces all are part of what we need to be able to deliver.
Thanks. And do you see that we're keeping up in the security requirements as much as the core technologies for that connection to IoT, if you will?
No, security is honestly our biggest concern, right? Being able to trust what's happening, the data is going through, and zero trust architecture is all about ensuring that we're able to have that trusted partnership in each of these handoffs, and especially for our systems, especially for the capabilities and the criticality of what we're able to provide, we need to be able to trust the product that's protecting all this information. And so that's one of the big barriers that we're going to have moving forward is how do you have that trusted entity? How do you have access to the state-of-the-art foundries that are oftentimes on different countries and different soils? So that makes things much more difficult to providing that cutting-edge capability into the hands of our warfighters, and we've got to figure out how to bridge that effectively.
Great. So I think as we have a call to action at the end of this, trust will be one of the key words, I think, that comes out.
Absolutely.
So also in these future commercial technologies, we're seeing a massive growth in data, artificial intelligence. We talked about AR, VR, machine learning. They're really rapidly changing the landscape in everything we do. Mike, what do you see as the biggest challenges and the biggest opportunities in these areas over the next decade?
Well, it's a multifaceted problem. Of course, capturing the data in the first place, having enough storage wherever you're at, but increasingly bandwidth, the ability to move the data around is expensive from a standpoint of energy. It's from a standpoint of consuming available bandwidth. And then compute as well. Now, compute has become a smaller fraction of the total because we've been able to advance compute faster than we've been able to advance bandwidth. And so getting to balanced systems, as I said earlier, I think getting to more compute near the data, distributed within the network, as opposed to trying to bring everything to a central location, I think that's one of the trends that we see continuing.
Great. Thank you. And Ahmad, I think, TI clearly works in the area of balancing systems. can you add on to that from standpoint of all those technologies?
Yeah, obviously, yeah. Absolutely, Dave. I mean, as Mike mentioned, I mean, AI is a big part of a lot of these systems as far as the bringing intelligence to the edge, and not just the cloud and kind of central systems. But also we understand that AI has been pretty much evolving over the last several decades, and it's more like evolution to me than revolution. I mean, it's a very big hype and it's very important for us. But you know what made AI so interesting for all of us over the last many decades is the fact that, you know, the more processing power and the more data we have, the more we can get out of it by using some of these AI algorithms. And obviously that processing power improvement and availability of data has been evolving for quite a while. So it's not like I don't think it's a step function. It's more like a revolution than a revolution. But also for the same reason, and kind of related to security question that you brought up, is that, you know, the quality of data matters a lot, because in many cases, you have seen that you feed the data without kind of verifying the quality of data and get the wrong conclusion. I mean, there are many examples in industry and even in social networkings and many aspects of it. Even AI algorithms right now, some of the algorithms could be very much vulnerable as far as the adversarial attack by kind of manipulating data to kind of mislead the AI. So as much as it brings a lot of opportunities for us, also it brings a lot of challenges for us, and it's part of the evolution. The fact that we wanted to distribute the system, then we make it more vulnerable to kind of all the attacks and all the security concerns. And then you bring up the issue of connectivity and latency, because we demand for more data and more availability of data at any point. Then power consumption becomes an issue because you have processing at the edge. You're most likely running off a battery in many cases, how to make it more power efficient. So it kind of brings a challenge on every dimension of ecosystem of semiconductor technology and microelectronics, which makes it quite exciting and keeps us busy for quite a while.
Yes, it does. It's very exciting, and I think requires a lot of collaboration to get there. But you know, things that, you know, Mike, you mentioned bringing compute to closer to the data and that sort of thing. And we hear a lot now about neomorphic and quantum computing and other future applications. So, you know, I guess for what applications do you see these being used, and when do you see both of these as viable capabilities?
Yeah, so neuromorphic and quantum have been around as concepts for quite a long period of time. Mm-hmm. There's certainly systems out there today in both realms. Each of them has some notion of an application. And in the case of quantum, I'll start there. We have systems today that can run quantum algorithms, but not the cool science fiction things that people are expecting to see. And so there's a bit of a gap between the capability of systems we have today and the capability that people think that they should have today. Back to the notion of internet time. I think from a quantum point of view, depending on the algorithm, we'll be able to do things with material science simulations within, let's say, the next 5 years, and some of the broader applications in maybe 10. Factoring really large numbers, cryptography requires the most resources, and so that's potentially further out. But I think we're making steady progress. I can't predict how steady it will be over the next decade, but I'd say about a decade for now for the kinds of commercial applications people have talked about. Neuromorphic, it again depends on the application. I think people gravitate to sort of real-time, let's say reflex-like applications like robotics, but we're finding that there is a broad range of algorithms that work by essentially reinforcing different variables. So constraint satisfaction is one that we're seeing. You can get to a heuristic answer very fast with not very much energy. It may not be mathematically the perfect answer, but in many situations, getting to a good enough answer quickly is really the thing that you need to do. And so I think we're within 5 years from commercial applications along those lines. We have a vibrant research community, including some commercial participants as well. And so I'm, from a timeline, more optimistic about neuromorphic.
Fantastic. And Annabel, when you think about all the applications in IoT and across the defense space? Do you have any science fiction applications that, neuromorphic or quantum is being addressed, looking at?
A lot of I think what Mike talked about is really what's in the realm of the possible, and the more that we're able to show and demonstrate the capability and the things that are nearer term, the more that I think our researchers can really think about what's in the realm of the possible and in the future and beyond. I think one of the challenges that we'll have, particularly in our industry, is this trust and trusting what the machine is telling you. And I think that's more of a human mental type of issue that we're going to have to overcome in order to adopt these tools and practices in our day-to-day lives to help analysts, help users really help digest data and provide actionable intel. I think there's several leaps that we'll have to take in order to get to that point.
Right, and trust in the data and the volumes of data being transferred. Doug, can you speak to the system requirements for, that transfer of data and how that gets addressed?
Yeah, I think there is an opportunity, and it was mentioned before, where, at the other end of the spectrum from large algorithms, large AI processing, at the other end, if you get more towards the IoT things, the sensor end of things, there's a couple of aspects. One is having very efficient, very compact algorithms that can be trained and learned and processed to reduce the amount of data at the edge that gets sent back through the pipe. And so if you think of thousands of IoT devices connected, working through the same bandwidth, all and trying to preserve very low power forms, a lot of work has to be done at the edge to do local processing. Think local speech processing, think diagnostics, and send back the answer, as kind of was stated before. But the other piece of it, the other benefit to putting some of that machine learning AI kind of at the edge, maybe something that can run on a system on chip, is to optimize the performance of the pipe itself. And so, if we can continue to have active control when interference comes in, that kind of thing, and preserve the high data rates that you would have in an ideal situation without interference or something like that, make that adaptable. The smart RF chain, that type of thing, you can preserve the pipe itself while you're also optimizing the amount of data that goes through the pipe.
Fantastic, thank you. So let's take it a little bit then from the future systems and those requirements down a level, maybe to the microelectronics itself. So the United States technology superior has been well rooted in a constant progression of technology, Moore's law, if you will. So I think I'll start throwing a softball to Mike on Moore's law, but then see what others think about it as well. Semiconductor development has followed Moore's law for several decades, and in more recent times, it seems to continually morph, to change and stay alive. So what breakthrough technologies do you see as needed to continue Moore's law trajectory, and is it necessary? Mike?
Yeah. Indeed, we've gone through essentially sort of sea changes in technology about every decade or so. The 80s were around inventing lots of novel devices, memory technologies, and so forth. Achieving essentially at scale in the 90s, the beginnings of material integration in the O's. We're currently in an era where we're integrating materials, structures, and architectures together. It's not simply about making smaller CMOS transistors. And indeed, when we shrink a CMOS transistor today, we typically make it worse from a performance point of view as we're achieving higher density. And so figuring out how to both make up for that performance difference and then use all those transistors architecturally is part of the present. Now, if we look into the future, maybe a decade or so, the challenge of power scaling has come back again. This is at least the third time in my career that we've run into power scaling problems, and each time we figure out different ways to overcome that. The second is two-dimensional scaling is slowing, and we're building up into the third dimension. And again, there's an architectural problem of how do you take advantage of the available wiring density and things of that nature. But beyond that, there's been a bunch of promising research around novel kinds of beyond CMOS devices. Now, they are not necessarily drop-in replacements for CMOS, but they would enable heterogeneous architectures. And I think that is also let's say a decade from now, something that we'll see on the shelves today.
Great, and I think certainly the others, Ahmad and Doug, can talk to the beyond CMOS devices. So, Ahmad, what are your thoughts on continuation of
Yeah, that's a very interesting question because it's kind of hard these days to understand exactly what we mean by Moore's law because of semantic discourse we have on the topic. Because, I mean, are we looking at the power, transistor count, speed, dollars per transistor? I mean, all of these have different trajectories. Or even, I mean, these days, the definition of processing nodes varies from one domain to the other. It's no longer just gate length and half pitch. I mean, it's becoming more and more diverse in terms of the meaning of the Moore's law. And that's why we see this kind of spectrum of some people believe it's already slowed down. Some people say it's not changed. And they all, depending on what I mean, might have some different flavors of the Moore's law. What I fully agree with Mike on is that I don't think it's going to be just CMOS scaling only. I mean, we are talking about 3D integration or 3D aspects or heterogeneous aspects, and it's more a monolithic 3D as well as SIP 3D. And what I mean by that is we see for many applications, scaling the CMOS is not necessarily the best solution. I mean, for example, for a lot of power management applications or some analog applications that really requires the voltage swing and headroom and signal to noise. I mean, of course, we can squeeze it in and compensate for that, but it's not the ideal scenario. So really in the future, I see that many technologies coexist and it's not going to be a single vector, it's multiple vectors. And we have heard quite a few of them, even in this panel session. For example, 3-5 materials. I mean, things like GaN and indium phosphate or some other technologies that are good for RF or photonics. Or even silicon germanium, an excellent technology for many applications in analog and even some applications for sensing. So we see that many of these technologies coming together in a way that from user viewpoint still looks like a single chip in many cases, but it's really convergence of multiple vectors that drives this initiative. Because if we try to keep squeezing everything in CMOS, we may address some needs of some applications, but it may not be the optimum solution, considering the fact that when you get to these very fine nodes of technologies and with the large wafer sizes, there is only a few markets that can take advantage of this scale. And many other markets like analog and mixed signal and RF have different needs that really can benefit from CMOS integration with other technologies. So I really see the future is not necessarily a single vector evolution of just one technology in CMOS. It's going to be multiple vectors. And convergence of them can bring a lot of value. And it could be monolithic, could be heterogeneous at packaging level, and brings a lot of challenges into interconnection of the dies and how to interface these together and high-speed interface between different chips within the package and between the different pieces of the silicon and other semiconductor materials in the package. So I think we have been used. We are used to kind of like many decades of almost a single vector scaling. I see in the future we see many different vectors coming together and add value in addition to CMOS.
Great. And Doug, do you want to comment on 3-5 materials aspects of that?
Yeah, and I would agree with what Ahmad said. A lot of this is as we look to optimizing an overall functionality. You know, you see several things. The silicon is getting far more capable. Back to an example of an RF chain. Digits are you can digitize things very directly and out at the edge of the circuit. So, but to close a link to really make performance and like I mentioned before, preserve the high data rate. There is a need for the efficiency that a 3-5 material brings, both in the transmit side and in a lot of cases in the receive side as well. So given the level of integrations increasing, the fidelity of the waveforms have to maintain very high. We see very much a need for some of the heterogeneous integration that Ahmad mentioned and Mike was alluding to before that. And so a lot of this, to bring this in place, and this is an area where I think, you know, the commercial industry is leading things, but from a U.S. government standpoint, would be a primary area of maybe focused investment to build a version kind of that would meet U.S. and military needs.
Great, thank you. And Annabel, as a user of these and builder of very complex systems, how far along are we in heterogeneous integration from the aspects of your requirements, and where does that need to go?
Yeah, I think there's still work left to do. The development timelines for some of our traditional defense products take a very long time. And so I think part of our challenge is making sure we accelerate timelines so that we can take advantage of some of these capabilities so that they really are cutting edge when they get to the hands of our warfighter. That's certainly one of the challenges that we have. And I think trust is the other challenge with a lot of these devices is how do you ensure that there's trust down to this level so that we can ensure the overall security of our systems, security of our data. I think that's another challenge. We've talked about it a little bit already on this panel, but that's our biggest concern, to not lean too far to the edge, because we've got to solve some of these key problems before we're going to jump all in.
Particularly with the heterogeneous devices being packaged together, I guess. Yeah.
Correct.
So we talked a little bit about materials and structures and architecture and packaging. I'll come back to Ahmad. What microelectronics technologies would you consider to be the most promising for advancing microelectronics over the next decade or so?
Yeah, I mean, back to the kind of previous question and discussion we had, I don't think we can just kind of focus on only one and consider it as transformational for everything. It's going to be a list of technologies, and they are all, I think, equally important for several reasons. I'm going to articulate as much as I can. Let's say, okay, we need more processing power. So we need to continue this kind of like Moore's law-like activities, more processing, more capability to drive more logics into the chip, and higher speed and more efficient I/O. But at the same time, we need to interface this to real world. And that is where analog and mixed signal comes to the picture. And many of those applications not necessarily need or kind of like drive some of these aggressive scaling, unlike like digital processing. That's where we see that technologies that are analog friendly are going to be on the rise. And we mentioned some of these 3.5 materials. For example, in power management, we see GaN is very promising. Of course, GaN has been around for quite a while, but GaN on silicon, which takes advantage of the silicon manufacturing capability, is going to be great. And we see a lot of opportunities because the kind of high frequency that we saw in RF and other systems didn't happen in power management because of the fact that when you go to those high frequencies, you lose the efficiency quite a bit. And GaN is going to bridge that gap. And of course, there are other technologies we see like silicon carbide. I think BiCMOS has many opportunities to drive innovation in many areas of mixed signal. Photonics on silicon, I think, is another area that with structured light and more sensing devices and a lot of even biosensors requires more integrated solutions at the photonics level. And in some cases, having expensive 3.5 materials is not as practical. So integrating that closer to the silicon is an area that I think is quite exciting. MEMS technology, we see transformational activities on MEMS for the range of applications from sensors to light processors and many other areas. And one topic that I wanted to highlight, which is not just one technology, but the fact that manufacturing, I mean, if you look at the semiconductor over the last many decades, we talk about Moore's law, which is kind of important, but reality of is that a lot of other innovations on manufacturing really made silicon so affordable. We managed over the last couple of decades to improve the yield almost 10x, we improved the throughput almost 10x, and increased the size of the wafer almost 10x. So we are 1,000 times more efficient than the past, and that's thanks to how, as an industry, learned to do semiconductor manufacturing more efficiently. And a lot of innovation goes into those continuation of the manufacturing capabilities. And we can come back to this question or this topic later, but sometimes we don't put enough value on how manufacturing plays a role on this whole kind of ecosystem of innovation. So my answer would be like a list of technologies that come together, and I'm not including software and other stuff. It's kind of a different domain, but it's more likely some of all these innovations that really makes it exciting, not just one vector that kind of like overshadows or dominates everything like what we are used to for the last couple of decades.
Thank you. And we will get back to the manufacturing question in just a minute, because that's clearly one I think of high interest to the group. But we have one question from the audience that I'll throw to Mike is, we're almost at the 3 nanometer technology node. And clearly we've talked about the difference in definitions of technology nodes between logic, memory, and other products. But when do you think we'll reach the sub-nanometer node? Mike?
Well, if the marketing groups had their way, we'd already be there. I saw a summary of a paper that they had basically taken the gate oxide thickness and they'd used that for the name of the node, which was something like 0.3 of a nanometer. Anyway, we are running at dimensions that are measured in a handful of nanometers. You know, the lattice itself of the silicon is about 0.5 nanometer. We're at a point where you can theoretically make devices smaller, but the ability to make them in the quantity of trillions is problematic. Now, there are potential techniques to basically grow devices in essentially a deterministic way, using chemistry, for example, and we're starting to apply some of those techniques. But there is, if not a hard step on actual density, there's not necessarily a hard step on effective density that you can achieve. Going to 3D, for example, as the NAND memory people have done, is effectively a way of packing more function into a given 2-dimensional space by using the 3rd dimension. So there's only a soft limit to what we can achieve from an effective density point of view, and that's really economics. The hard technology things are things that we've seen coming for a while, and we continue to operate closer and closer to the edge. I mean, there are physical limits, of course, but there's a lot of room between us and the physical limits.
Okay, thank you. So I think, you know, we've historically seen the role of large corporate labs and other entities such as IBM Research, Bell Labs, and others leading in developing the disruptive technologies. Without this type of corporate infrastructure, what does the U.S. need to do to continue to innovate and develop the next disruptive technologies? Annabel, do you have thoughts on that?
I do. You know, I think a lot of what we've been talking about is how we leverage what's happening on the commercial sector, which is all well and good, but defense has very unique needs and very unique limitations and unique requirements we've got to answer to. And without the government's concerted effort to bring industry together to drive addressing these needs, I think we're going to be left behind. And so that's really where we're looking to the government to help bring together the right entities, bring together the right research. Something like DARPA chips is a great start in that direction. It's not just about the capability and the performance, which is critical, but also the price, right? Cost sensitivity is something we're very much high on, and it's not just the manufacturing cost and the unit cost, but the ease of integration and then the longevity of being able to sustain systems that are often used for 30 plus years. And so I think that's where we really need the government's focus and the industry partnership to be able to work through and address these from a defense industry perspective.
Great. And I guess I'll stick with you for just a second. What do you see the biggest challenges to domestic microelectronics innovation?
You know, I think part of the challenge is the drive and the business case behind it, right? A lot of the business and the volume is largely on the commercial side. And if you look purely from a return on investment perspective, it's hard to engage the right minds to put the right resources, the right minds behind addressing our unique needs. And I think that does require a different emphasis. It can't just be about the dollars at this point. It really is a matter of national security that we're looking at it from a different perspective and bringing together a different impetus, a different inertia to help drive innovation domestically.
And Ahmad or Doug, do you see any other specifics in areas that where the U.S. is?
Yeah, Dave, actually, I think the fact that we don't have Bell Labs and IBM Watson, and I remember from my days in Bell Labs, the most important thing that I noticed there was the critical mass of experts. And that's very hard to find in a, let's say, single university or a single company, maybe on one topic, but not on as many topics that places like Bell Labs and IBM Labs kind of like supported. And a lot of these innovations we see, from smartphones to many other consumers and industrials, are based on technologies that really were kind of evolved and developed in those environments. And we don't have those today. And especially when it comes to, let's say, a material science research, which is critical for many of these new devices. It's a long process. It's an expensive process. And in the absence of strong support and strong, critical mass of researchers, it's very difficult to make breakthroughs that can really change the scope of the industry 10, 15 years from now. And it's very critical for us. In fact, we see that Europeans are now starting kind of copying things like Bell Labs by IMEC and the kind of the like type of, research institutes, bringing experts in together. I think with a lot of initiatives in DARPA, we have a chance to drive it, but we need to bring enough experts. I mean, if you go to any top schools, there are top experts in one field, but 2 or 3. And in Bell Labs, you had 20 or 30 or 100 more. And that's continuity and the availability of resources and equipment and all that stuff. So I think it's very urgent to build that critical mass somehow. Doesn't have to repeat the same Bell Labs story, but kind of something that is more tuned toward the new century. But it's more important than before to kind of break the barriers of the technology 10 years from now. Because if you look at all the demand for data and all the demand for power efficiencies and everything, the way that you can extrapolate it, we see we get to the boundaries of a lot of existing technologies. And if those breakthroughs don't happen and don't work on it now, we may get in a situation that something has to give and compromise.
So clearly with a need for that talent, Mike, I'll ask you, are there additional educational or workforce challenges to maintaining domestic leadership in microelectronics?
Yes, there are. Let me set it up by building on the previous point. When I talked at ERI 2 years ago, I talked about economics and technology, and how they have to both be satisfied to essentially bring innovation to enough scale that people could take advantage of. I think there's a third element which ties to this talent question, which I'll call, for simplicity, ecosystem. So if you look at some of the the economics, there's this whole notion of specialization. And then if you're not specialized in something, then you outsource the remainder. What that does is it creates a distributed ecosystem over time. Our current education system, particularly for graduate school, is focused on creating typically specialists, not necessarily generalists. And so we run the risk of creating these isolated islands of talent, and then figuring out how to bring them all together in one place and work on a problem that really requires multidisciplinary approach. That's one of the challenges that we face today. Often, people come in from different fields, they speak equivalent to different languages from technology point of view, and getting them all in one place and working on the same thing is a hard problem. No single company, for example, can work on every single thing. So figuring out a mechanism where, for example, the government can encourage parties to participate together, to combine expertise, all the while figuring out how to essentially reap the benefits of that collaboration. I think that's an important challenge that we need to work on collectively.
So clearly that's an area that I think there's opportunities for partnership, government and industry and academia on creating the future workforce. Thank you. So clearly foreign investment has shifted the locus of manufacturing. And, I said we wanted to get back to this manufacturing question. And some say it's difficult, if not impossible, to maintain R&D and long-term innovation leadership without a strong manufacturing base. I guess I'd like to start with Annabel. What's the industry's view on the Chips for America's Act? It seems to have strong bipartisan support. What are your thoughts on that?
A lot of what Ahmad and Mike talked about, research and development in this country, I think is critical. And the Chips for America Act is something that is a legislative approach to try and ensure that we have those right approaches, that we have the right incentive and the right focus, so that we can develop not just domestic capability, but the manufacturing wherewithal to be able to produce it in country. I think that also helps address the security concerns that we have as an industry, but it really looks at that necessary step to develop and expand and modernize that infrastructure that we need in the U.S. That has gone offshore in the last several decades.
And can we bring it back? Does this create opportunities for government and industry R&D collaboration and even manufacturing collaboration? And what might those look like?
It does. What we've been looking at in the Chips for America Act is really specific grants that the government is looking to enable in these specific industries and specific research so that we can develop that capability. And so you really can't do anything without dollars behind it. And this is a way to be able to authorize that and enable it into this industry that is lacking those types of resources, and really be able to focus the wide group of expertise that we have across our country to attack this problem.
So we bring some of the necessary dollars and expertise. Doug, I'll ask you, what do you think are the biggest challenges and benefits to partnering with the government on national security relevant research and development?
So we have found that very advantageous. So what we have done, and we have both a commercial model and a defense model. Our defense model is both. It is really provides access to open foundries for 3.5 gas and GaN. Either a foundry model where a customer will do their own design and we'll fab it for them, or a model where they will come to us for a design and we'll do the design work for them as well. And so for that, largely for that reason, we've kept our 3.5 fabs in the U.S. And that does open us up to partnership with DARPA itself. We have several initiatives running with DARPA, either directly or through some of the larger defense primes. And we also have been working with some of the labs to work, different advances in technology that may go enable a different mission or a system to be architected in a much more optimum manner. And so we see a lot of benefit with that. The challenge gets to be, we do a lot of silicon work too, and of course that's part of every chain, every system. But on the silicon side of things, we're in the same boat as everybody else. As was stated before, I think you said the locus of manufacturing and advanced processes for silicon have moved offshore. And we're right back into the same trust question, the same assured supply question as we talked about earlier. And so we're seeing benefit. Now the challenge for us, what we're trying to work through is how do we provide that same level of assurance, trust, collaborative development with the government on some of the silicon functionality, and to an extent the packaging aspects of it too, that we can do on the 3.5 side with our onshore, our U.S. fab model.
Great. So we see, a call to action for working on trust, on security, on bringing manufacturing back, and maintaining the development and the innovation practices. And I guess I go back to Ahmad and say, what best practices can you take away for protecting intellectual property in an increasingly globally competitive environment?
Yeah, we are all used to kind of filing a patent and, feel comfortable that, our IP is protected for a while. And these days, by having a patent, pretty much you're telling everybody what you're doing. So I think what's happening is that innovation and the pace of innovation in our field is so accelerated that really the best way to preserve or maintain your differentiation in protecting your innovation is to do more innovation. Pretty much staying ahead of competition by continuously innovating. Of course, filing patents and making sure that you have some protection around that is important, but definitely it's not enough because with all the consolidations, all the globalization of technology, and the fact that we have so many talented people working in our field, and ideas are coming up very quickly, it's very hard to kind of just file a patent and stay assured that nothing is gonna violate that. We need to stay on the treadmill of innovation continuously, and frankly, even some most innovative ideas have a much faster expiration date these days. So the only way to protect them is just keep going faster and innovate more. And that's why we need to have this kind of like foundational technologies to enable us to innovate faster. And as we talked earlier, and some of the panelists mentioned that, some of the key technologies they are dealing with today that is giving us a chance to innovate was developed a couple of decades ago. And we need to have that innovative approach to not only the application side and the consumer side, but the foundational technologies from material science, new manufacturing. And again, even on manufacturing, that's one of the capabilities that sometimes is looked at as an afterthought, but it can really bring a lot of opportunities for innovation. Some of the most complex machines that you see in the world, like EUV's machines, are the ones that are using in manufacturing. So innovation needs to be a continuous process, and the more you can protect it with handling the entire ecosystem, the more you can have this differentiation over the competition for a longer period of time.
Great. Thank you, Ahmad. And I think we're running up against our time, but final thoughts before I thank the panelists. What gives you hope for continued U.S. technology leadership? Annabel?
I think some of the things we've talked about, putting the resources, putting the thought process behind a lot of these ideas to help drive innovation where we need it to meet our needs, specifically for the defense industry. Chips for America Act is one thing, DARPA Chips is another, but it's really about identifying a problem and then coming together as government and industry partners to help resolve it. I think the fact that we're all coming together at a table and even at this panel to talk about microelectronics and the criticality of it tells us that we're looking at the right problems. Now we've just got to get the right smart people in the room to solve it.
Thanks. How about you, Doug?
Very similarly. I think that, step one is to recognize we have an issue. And so I see us very much waking up quickly and realizing that we have an issue, but also, what the depth and the extent of what that issue is. So that's refreshing to me. It gives me hope that we are going to put the right resources in place, get the right people together, and turn the corner. And, just the idea of the ERI itself is right along those lines. And so we are seeing more opportunities for collaboration, for research in a few areas. And again, that's been very refreshing and a great opportunity to kind of turn some of this around.
Great. How about you, Mike?
Oh, I absolutely agree. I think we have tremendous talent once we all agree on the problem and begin working on it together. I think that it often takes us a while to get aligned, but then I think as a nation we can move fast once we've accomplished that. And we have been able to accomplish really great things over the decades that I've been in the industry. And so I have confidence that we'll be able to do it again.
Great. Ahmad, how about you? Closing thoughts.
Yeah, pretty much the concentration of talent and the inspiration of people to come up with great ideas and the success that they are pursuing has surprised us over many decades. I mean, whenever we had this Sputnik moment, the innovations put us in the position that we lead the pack and we come up with the greatest innovations. And I think we have all the tools and all the talents, and by putting it together and supporting it through this government or initiatives and working together on some of those innovative ideas, we have a great track record, and I'm sure we have a lot of potential to lead for a longer period of time.
Thank you, Ahmad. Well, in closing, I'd like to thank all of the panelists for such an informative discussion. I wish we could go on for another hour, but I also want to thank DARPA at least for letting us run over 5 minutes or so. I hope we've been able to give the attendees a better understanding of the opportunities and the challenges facing both the technology and defense sectors, and the potential opportunities for government industry collaboration to secure the supply chains, protect intellectual property, and long-term access to leading-edge manufacturing. Thank you to everyone for joining us, and please enjoy the rest of the ERI conference. Thank you. Thank you, panelists.